Okay. Thank you to be here for the lecture of today. Today, we will reconsider free and false answers, or the free and false answer. But the idea is to show you a system of second order, and more in general, some aspects, some particular aspects of the free and false answers for a system of the second order. Second order means two states. We will see that when we will consider nonlinear systems. Typically, we don't speak about order. We speak about number of variables, state variables. When I speak about variables, I intend most of the times state variables. Yeah, just an introduction, then we will reconsider the characteristics of system with two or more states in a more structured form, I would like to say. Okay, let me, excuse me here, let me switch on the lateral camera and let me start with the presentation of the lecture of today. As I told you, the system consists of two states, or state variables. One second, because here I don't have enough space to. And let me switch on the lateral camera and let me start. As I told you, until now, we have seen systems with just one state variable. Do you remember the car? We consider also the aerostat system. The aerostat system, I think we considered. I don't remember really. Should I look? Let me see. I remember very well the car. But I think, yeah, independently what we have seen until now, we have seen basically the system with one state, and then we have seen a system with two states, but I remember we considered aerostat system, and we considered also the car. Do you remember this? This was the last exam. But this system here, with two states, remember, position and velocity. The position states the work, the velocity states the kinetic energy. Both are forms of energy. But what is the difference with respect to what we will see today? In this case here, as I told you, we have the work. The work is an energy, but it's in a particular form of energy. Graphically, in the block diagram, we can see that this work, in this case, in this particular case, can be seen as an effluent integral. I mean, we don't have a feedback between position, which states, in this case, the work, and the rest of the system. This is a particular system of the second order. We are in the present, at least we have seen just, how possible to say, a linear case of this, without considering nonlinearity of connecting with the friction, even though I told you about the nonlinearity, but it's not present yet. But we don't have here any feedback from this form of energy, which we have here, the work, and the rest of, let me say, the dynamics. We will see today the system, an electrical system. We will see in the future also a mechanical system, quite similar to this one, but in which this variable here is connected with the rest of the system. This, yes, is the system of the second order, or let me say two variables, because we have two energy, but it's in a particular form of the system, because we have basically no feedback between all states. Here, from here to the system, we don't have a feedback or the connection. We will see now what to change in case, now I am considering an electrical system, and then I will show you also a mechanical one. What happens if we are in the presence of a feedback from, let me say, feedbacks between states? Look, this is the system. Basically, is an RLC circuit, in particular form, but it is an RLC circuit. Probably we have seen in electrotechnique such kind of system. Probably we have seen in series form, in parallel form. Here is not exactly this, a little bit a combination of both. I would like to consider this because probably at least the model we have seen for the other system. But the dynamics, basically, the analysis of the dynamics, also the characteristics are quite similar, or I would like to say structurally the same. Look at this. I orient the system in this form. U of t is the input. The output could be UC of t, but could be also I1 of t. Could be any kind of variable, not necessarily state variables, which I can, let me say, consider in the scheme here. Everything could be IC, could be IR. Do you remember? Could be, I did input here UL. We have seen also in the last, I think, I don't remember when, probably at the beginning, we have seen that I can also consider UL, any variable, believe me, not necessarily the state variable. Which kind of state variable we are? What about the state variable? You remember this question we already answered in different contexts. We have here I1 and UC as state variables. Why that? Because we have two elements. The inductor with its inductance, the capacitor with its capacitance. Please pay attention. Sometimes, as I told you last time, I say inductance instead of inductor, or inductor instead of inductance. Typically, I say inductance instead of inductor. It's not an error, but to be precise, we should say capacitor with its inductance. But the inductance, nevertheless, is the physical characteristics of the inductor. This means also to simplify the nomenclature is not wrong. We have two elements, coil, inductor, if you want, and capacitor, which can store energy. Can store energy and can give back to the system the energy which is stored. This means you have two variables to be considered to describe or to represent or to reflect the energy which we have in the system. Yeah. Again, we have electrostatic and electromagnetic energy, two independent energy. About the concept of independent, I already told you a little bit also last time when we had to do with kinetic and the work. Here is more explicit the concept. First of all, we have two kinds of energy, electrostatic and electromagnetic. Already the nature represent an independence because they have two kinds, two totally independent energy in this sense here. But also the topology, even though I have, for instance, two inductors, depends the topology of the circuit in order to say if the two energy, even though they have the same nature, they are dependent or not. Do you remember? If the inductance is parallel, of course. Or let me say, if anyway, if the easy example, if the inductors are in series, they have the same current. This means they are depending. If they have parallel, and in the same sense, Rhine parallel, pure parallel, they have the same voltage, and then we can see that they are depending too. But anyway, the topology states the dependence and independence, of course, together with the structural nature of the energy. In this case, no doubts, because we don't have a parallelism. We have just L and an inductor and a capacitor. This means the energies, the two energies are independent. Independent, as I told you. If you think about a series two, LRC is not the case. So in this case, even though they have the same current, we have two independent energy, because the nature of this energy is basically different. Kirchhoff balance, U of t equals UL, which I didn't put, but you can imagine if you want, I put it. I didn't put because it seems to be that I don't have much place to do, but it's here. No? Let me correct in this one. This is UL of t, and L I will put here. No? It's clear what I mean. Kirchhoff balance. Now, if you remember what is the meaning of what we want to obtain in the context of system theory is two equations, because we have two states, functions, two equations in which just states or the state variables and input are present. You remember this? Or at least in the representation, the physical representation of this. Yeah. Look at this structural equation here, which we learned in electrotechnics. UL, which I indicated now, equals L multiplied the derivative of L with respect to the T. IC, the current of the capacitance, we can see here. No? UL, I indicated exactly now the voltage on the inductor. You see the voltage on the capacitor or capacitance, as I told you, is C multiplied the derivative of UC with respect to the time. I don't insist on this two, let me say, definition or structural characteristics, because you learned in electrotechnics. IR, also in electrotechnics, is Ohm law, is the voltage UC divided R. Using this Kirchhoff law and this three let me see, structural equations, we can build these two equations, which we have U of t, which is the input can remain, because we look for two equations in which should appear input and states. Basically, the elements which characterizes the energy, or better to say, the element which energetically characterize the system. As I told you, I1 and UC characterize the, let me say, the internal energy of the system, and U of t is the, let me say, I don't know if it's, I would like to say the energy which is an input of the system. Of course, we can consider also the energy which is go out, which we lose, let me say, or we dissipate through the resistance. But again, IR is a function of the state. of course, also of the input. This means it is enough to have, let me say, the expression of energy, which plays a role here. Just considering the energy in the inductor, the energy in the capacitor, and the energy in input, because this energy here, which is, let me say, go out, is a function of the three kinds of energy. Look at this. U of t remains. UL, we can consider this one. UC is exactly UC because it's itself the state. This means this equation here is exactly well represented. Why that? Because we have input and the two states already present. The state I1 is represented through its derivative, the change of energy. The second equation which I am considering here is the node balance on this node here. Basically, here we say that the current which is going into this surface, so that, yeah, you can consider a closed surface node, equals the current which is go out. This means IR plus IC. Probably you know better than me. Now, as I told you, here I didn't indicate the second law of Kirchhoff, but anyway, this is the way to represent the circuit. Now, also here we have to consider states at input, if any. Again, considering this structural equation, we have this I1. Here I must be not, let me say, replaced. IC is basically C multiplied the derivative of C with respect to dt, and IR is UC divided R. Now here, in order to save time, I express directly in the system theory form this equation. Once try to do together with me. I1 I don't need to change because it's the state. IR I can express as a function of the state in this form here, UC divided R. IC is exactly this one. This means, do you remember, the goal is to obtain the equations in form of the variation of the energy equals what this variation, or let me say, the element which this variation generate. And from here, this variation can be seen U of t minus UC divided L. From this equation here. Here, if you consider what I told you, plugging in where I need here and here, these two equations, I can write in the same way that if you think about this element here will become C, the derivative you see with respect to the time, I can consider the variation of the electrostatic energy, which is reflected by IC through the derivative of the voltage with respect to the time. This means the derivative of the voltage with respect to the time, which is here, is I1, we can see here, minus IR, which is represented through the state you see in this form here, UC divided R, everything divided by C, because C originally was here, we can see. It's a little bit written very fast, but we can see what I intend. We can see what I intend. C multiplied DUC with respect to the time is basically here because of this position. I divided by C, what? I1, which remain I1 because it's the state, minus IR, which is in terms of state, UC divided R. Everything divided by C. UC divided R is the current IR. But very important, as in electrotechnique, everything came from this equation and this equation here, which are both the Kirchhoff law, or represent both these equations represent the Kirchhoff laws. Look now what I'm doing here. Of course, this representation is the representation which can be used. We will see. We have already seen a little bit that these expressions can be very suitable if we consider the matrix. To remember A, B, C, D. In particular, in our case, A and B. To remember, I told you a lot about the matrices representations. Now, let me recall some knowledge in mathematics. Instead of these two equations, I can equivalently, in more mathematical sense, again, with this form here, do you remember, I told you the method which we will reconsider later, the method which use matrices. Forget for a while, let me recall the mathematical, let me say, knowledge, because as I told you, this course is in a mix between mathematics, which you already know, system theory and control, dynamical systems. Why this form here is basically equivalent to these two equations? It's relatively easy. If you do the derivative of this equation here, I can always do. Remember, the function f1 equals the function f2. This means the derivative of the function f1 equals the derivative of the function f2, assuming that the two functions are differentiable. This means the second derivative of this expression equals 1 divided c, the derivative of I1, minus 1 divided R, the derivative of UC. Clear, no? Now, if I plug in here this expression, believe me, we obtain this expression here. We obtain this expression here. Please pay attention, don't make mistakes. Therefore, I already prepared this slide, assuming that I didn't make mistake, because it happens. Very often we are using, in general, symbolic toolboxes for MATLAB or for mathematics in order to avoid mistakes. But just to understand, this element here is this expression. Let me see. This expression here is basically 1 divided c multiply minus 1 divided R. On the other part is plus, we can see now. And then we have 1 divided c with multiply 1 divided L, which is this one, which multiply. I cannot see. 1 second. Okay, better, no? I don't know, it's better. It's better. Here, no? 1 divided LC, you see where this comes from. 1 divided L multiply 1 divided C is 1 divided LC. 1 divided C, excuse me, 1 divided C, we multiply this. We have 1 divided C, which multiply 1 divided L, 1 divided LC or the CL. Why this one with plus? Because here on the right side, we have this element with minus. This means I can bring on the other part and I can change the value. Why 1 divided LC UT? Yeah, because again, we have 1 divided C, which multiply 1 divided L multiply U. This form here is what you have seen in math, which we have the variable of the differential equation, second order differential equation, equal the input. If you want, in our distinction, we have on the right part the input or the cause, let me say, the input energy, the external energy which is going inside the system. And here, how change the energy, the whole energy, second order, but from the capacitor point of view. This is the interpretation of this expression. I put in input energies, and this energy is reflected in all system, in each part of the system, but from observed, analyzed, from the changes of the energy on the capacitance. We can do the same considering the energy, the point of view of the energy of the inductor. Why is the energy is full represented and described? Because of this second order. Because we have two equations, we have two variables which corresponds, this I told you at the beginning of the semester, of an differential equation of order 2. Yeah, a little bit abstract. I can improve also theoretically, but I don't want to do because we are not here really just for math. No? We are here for many other things. Let me consider excuse me. Let me consider this case in order to, the idea is to show you free and forced answer for a system of the second order. In order to be more concrete, I will present in a real case. But of course, I would like to start with good values. At the end, the values or the results will be not so nice, but at least at the beginning, I can say that the value which I consider is not so bad. No? Excuse me, I need to stop because I have to answer to the telephone. I come back in a few minutes. Please remain. In the meantime, look at this equation here. No, I come back. Okay. What I am showing here is basically just the expression which I had here with another notation. Instead of the second derivative in this form here, I considered dot. Probably you have seen also in math. Here I have a dot. The rest does not change, but of course I am considering also L equal 1, C equal 1, and R equal 1. Exactly as I wrote here. Moreover, to remember, in the context of a free and forced answer, I have to consider, please pay attention, the internal energy, which is reflected in the internal initial, the energy which I have at the beginning. This is reflected with the states at time 0 or at time theoretically, you learn in the Cauchy problem that it doesn't matter at which time I am considering the energy. Very important that I have. But of course, in engineering fields, we will consider the energy when I start to control, when I start to observe. This means, let me consider 0 as the start point is in a typical value. Otherwise, I can write 1, 1, 2, 2, and so on. Of course, in this sense, I will start from 1. I will start from 2. Second, hour, the time which we have here is relative to the unit which we are considering. Anyway, this problem now is known from math. What we can do now, again, the free and forced answer, which is a little bit different with respect to the homogeneous and non-homogeneous approach. But at the end, we have the same result. The advantage here, I don't know if it's an advantage. For us, yeah, for engineers, it's an advantage because we are more connected with possible simulations, or better to say, the simulation can help to interpret the results. Physically, I would like to say this approach explains more in depth what happens into the system. Therefore, we are speaking about energies. We are speaking about how possible to say, elements which store energy. Free prop. Very important in the exam. Please don't make mistakes. Please remember, it's easy to remember. Free means autonomous system. This autonomous recall as without input, without forcing element, without energy which is going inside the system, just to look how the energy in the system is evolving freely in autonomous form, zero. We characterize the equation by the notation free in the PEDIX. And then, of course, very important, this is zero, but the initial conditions are exactly what we had here. I mean, we can see that in the general problem, we have two, let me say, form of input energy, external and internal. Now, in the free answer, we consider just the internal one. U of t is equal to 0. It's exactly what I told you until now, but here we have this particular system. We will see that this kind of system, second order system in particular, can be solved, any kind of system in any case, can be solved very easy with eigenvalues of the A matrix. Do you remember the transition matrix, which represent exactly this lambda or lambdas here? But let me go ahead with this approach, which we have seen until now. If I assume that the solution of this Cauchy problem consists of this form here, use C free equal C is a constant. It's not nothing to do with the C here. No? It's a constant. Do you remember last time we considered a mechanical system which we didn't have any mismatch in the data in the notation. C is a constant. Exponential function. Sometimes I write exactly exp. But in this case, the exponential function up to lambda t. Why this choice? Do you remember in math? I don't want to go in depth because, again, here's not a lecture just in math. The exponential function is an eigenfunction. Remember this concept here, because the derivative of the exponential function reflects the exponential function again. We can see here. And also the second derivative. I mean, the derivative consists again in exponential function. Or if you have more than one exponential functions, we will see a little bit more in depth also this aspect here. But anyway, from here to here is clear. Why I am thinking that the solution can be expressed in form from exponential functions for this reason. Because the derivative of an exponential function is again something related to an exponential function. The system is linear. We can see in a combination of the derivative. This means I can assume that the solution here is again an exponential function somehow, which will, or a sum of exponential functions, which will, because we have a sum of derivative, which will consider these two conditions. Now, if I plug in exactly what we did last time, no differences, also in the assumption, the idea of the assumption and so on. If I plug in now these three equations, assuming that I will obtain this, I will obtain this. Here, I will have this expression here. Why that? Because we have here the second derivative, which is this one, assuming that u C3 consists of a function of this form or more than a function of this form. Here I simplified, and let me say a little bit the analysis, but in order to be more effective. Here we have the first derivative plus the first derivative is as here plus the function. Basically, this expression here. Again, as I told you last time, the exponential function is always positive. Oh, anyway, it depends on the c. Excuse me, depends on the lambda. But in any case, it's never zero. This is the concept. Exponential function up to lambda t is never zero. Of course, if you have a minus in front, let me say, of exponential is negative, but it's never zero. This means I can cancel. I can cancel in the same way c. Do you remember the reason is? The reason is if c is equal to 0, we have UC3 equals 0. But this does not satisfy this condition at 0. This means cannot be any solution for this kind of problem. Moreover, if I put c equals 0, in accordance what I'm writing here, I end up in a condition, an equation which states in a trivial condition, 0 equals 0. It's something that is not acceptable in the sense it's true, but it's not constructive. But the main reason is you see free of time for each time equals 0, does not satisfy this. I can assume that c is not 0. I can cancel, no? Because if it's not 0, I can divide it by c. I have this equation here. The name of this equation is, we will see also in the next lectures, is characteristic polynomial. I will find the solution of this, because the idea is to find lambda and to find c, or lambdas more than 1 and c. We can see that we have 2 lambdas. This means lambda 1, lambda 2 in accordance to the A, B, C formula. Or if you are more habit to work with the PQ formula, believe me, but this is from Gymnasium. We can write this, which equals -1 divided 2 plus minus j multiply root of 3 divided 2. No problem, because we have a root of -3, which can be written j, do you remember, is root of -1, which multiply root of 3. I think you remember from high school. No? Here we have root of -3 inside. But root of -3 can be written of j multiply root of 3. Why that? Because j is the root of -1. Now, look at this equation here. You see your free, it seems to be in accordance with what we found. Let me show you here. We have 2 lambda, as I told you before, lambda 1 and lambda 2. One will plus, one will minus. Now, in this analysis, I simplify it a lot, because at the beginning, I told you 1 lambda, and then it seems to be that you have 2 lambdas. I have a presentation in the next weeks. I will show you how we can more formally to analyze this kind of problem using matrices, for instance. But here, of course, we have two lambdas. Both lambda represent possible solution of my Cauchy problem. The system is linear. This means also the sum of these two exponential functions is this function, which is the sum of the exponential function, is solution of the differential equation, because we are in the case of in a linear differential equation. This is the general form, which we probably know better than me, or we learned from math, because both are solution. This means the combination of these is the more general solutions. We can see here. First element of the exponential function is in the function of lambda 1. Second is exponential function with the function of lambda 2. Of course, the combination of the linear combination implies two different constants. This is a little bit is explained a little bit quickly. We will see a little bit more in depth formally in the next weeks, but makes sense in the context of a linear differential equations, two lambdas, lambda 1 and lambda 2. This means we have two different, let me say, exponential solution, and the combination of both, because the system is linear, is again the solution, the more general. Think about intuitively, in this sense. Both are solutions. The system is linear. This means the combination. Combination means the general combination C1 and C2, which multiply the solution, the exponential function which reflect functions which reflect the solution, is again a solution, but the general one, because of course I can consider one, or I can consider the other one separately, but in general I can consider both together, which include both together, include all possible solutions. Now, what is the meaning of possible solution? We know this concept from math. I have to calculate C1 and C2 because I have in the free answer two constraints. Which allow to say which one between these infinite up to two solutions, which one is our solution, which is characterized in terms of free by these two conditions. Look, I'm considering the condition. Here we have a dot, even though it's not very well visible. Now, believe me, allow me to proceed a little bit quickly. If I do the derivative of this expression, of this expression, I will have this one. I will show you, because the derivative of the exponent function is again the exponent function. You know, this is lambda 1 with minus. This is lambda 2 with plus. But here, you remember, we have exactly lambda. If you want, we did this calculation here. Here is the lambda, here's the lambda, lambda 1 in our case, C1 in our case. Of course, here is the same. Here we have a lambda 2, C2, because we have a combination, as I told you until now. And here we have exactly lambda 2. The derivative, which we learned at school, which we learned in math. Look, why now these two equations? The reason here is somehow easy. Why that? Because using this expression or this condition, we have the UC at time 0. UC at time 0 is 1. If I put here 0, I have a C1, plus if I put here 0, I have a C2. Math, this expression. What about this? Now I will use this one with this condition, as we did basically last time. I put here 0 because it's given. Again, the problem is given. Excuse me, here. The free problem is given, fixed in time, equals why this expression? Because it's this expression calculated at time 0 plus this expression, which came from this expression calculated at time 0. Again, this means we can see where the system characterized by the variable C1 and C2, where this system comes from. From this equation, I have that C1 equals minus C2 plus 1, C1 minus C2 plus 1. From here to here is easy to calculate. And then I will plug in this, exactly, this C1 here, and I will obtain this 0 remains, of course, equals this part remains, which multiplies C1, which is 1 minus C2. I plug in here, as this is, plus this expression, which is here, which multiplies C2. Now we have the possibility to calculate C2. But basically, what is here? We have in a system of two equations, algebraic system with two equations in C1 and C2. The idea is to calculate C1 and C2 in order to obtain univocally the free answer, how the internal energy evolves for given internal energy from the point of view of the capacitors, but reflect the energy everywhere. I will show you in 1 second. From this equation, believe me, I do some easy calculations. I have to multiply. This is very boring. Try to do at home once or 2 times in order to be able to redo a similar exercise in the exam. This multiply this, plus this multiply this. We can see here, minus, multiply minus is plus. This is very boring. I don't want to explain because it's, you can do better than me. For instance, here, C2 multiply minus 1 divided 2 in this element here. C2 multiplied by this element is here, and so on. Then you have to look what I can cancel. If we have something to cancel, typically, yes. Or to sum up, we can see here. We will obtain this element here, just summing up this here, equals, I bring on the other part, minus 1 divided 2, which become plus 1 divided 2. And this is j root of 3 divided 2, because I am bringing on the other part this element here. At the end, C2 from here is j divided root of 3, which multiply 1 divided 2 plus j multiply root of 3 divided 2. Why that? This element is here. I will divide this element here by j multiply root of 3. Basically, we have here this element here divided j multiply root of 3. But j in the denominator, I don't know if you remember, is equivalent to minus j in the numerator. I don't know if you remember. Probably this I would like to explain in order to understand. Did you agree that we have this? I tried to from here. Math from high school. I divided by j multiply root of 3. This means this remains. Now, for some students, it's extremely boring. what I am doing. If now I multiply by j divides j, this means I multiply by 1, but in a clever form, I will obtain exactly what I told you before. J multiply j is -1. I don't know if you remember. Recall j is equal root of -1. No? This implies j multiply j, this means j squared is equal -1. Therefore, this minus here, which came from j multiply j. Just to recall everything from high school. If we have C2, I can calculate directly C1 from where? From here. It's 1 minus C2. 1 minus C2 means plus here, j divided 3, which multiply this binomial element. Yeah. Let me do some comments. Of course, I didn't, let me say, I didn't complete. I have to write the UC3, putting this boring, this boring expression here, and putting this boring expression here, and we have a very long boring expression. But this is easy to do, not just to plug in. You don't have to do also in the examination. Believe me, you don't have to do. Let me see if I did. Probably. No, I did. Excuse me, I did. I found in a slide in which I did. I found in a slide. This means let me show you this. It's boring, but I did in this sense. I would like to show you. I calculate C1. Do you remember it was, what is, I lost. Yeah. 1 plus this. This means 1 minus 1 divided 2. I don't know if it's visible. 1, if you do this, multiply this, is -1. Root of 3 I can cancel. This means 1 minus 1 divided 2 plus this j divided 2 times root of 3. Now, please pay attention. I did the calculation very fast because I multiply. I have here j divided 2 root of 3. If I multiply numerator and denominator by root of 3, I have in the numerator root of 3 and in the denominator 6. Why that? Because root of 3 multiply root of 3 is 3. Multiply 2 is 6. Try to do at home. No, I would like to avoid now to this calculation. If you want, I can do. If you want, I can do. But anyway, they are really calculations which belong to the high school. Should I do? We have C1 equals 1 plus this. I clarify. I already clarified this. It's boring. This I know that is boring. Look, 1 minus 1 divided 2, because if I do this, multiply this, I will obtain 1 divided 2. This is clear. No? j multiply j is minus 1, root of 3 or root of 3 I can cancel, and remain in the denominator 2. Now, if I do this product, I will have plus j 2 times root of 3. Can be written this form. 1 divided 2 if I do this calculation. Plus what? J multiply root of 3 divided root of 3, which multiply 2 multiply root of 3. Excuse me. This is in order to show you that I multiply by 1. No? If I cancel, I stupid because I didn't do anything. But in order to show you that I multiply by 1. This means at the end, conclusion, I hope to proceed a little bit faster. Because j root of 3 multiply root of 3 is 3. Multiply 2 is 6. Exactly this. I don't know if it's visible. No. C2 was already explicitly somehow calculated. I don't know if you see it. Now I don't want to do the same calculation for C2. Believe me, you will obtain this C2 here. This means this is the UC free. This is UC free. If I plug in now C1 here and C2 here. Do you remember C1 multiplied this was the general solution. C2 multiplied this was the general solution was C1 multiplied this plus C2 multiplied this. Now I particularize the solution considering my initial energy. And then the energy is going ahead. But the question is, this expression is quite abstract. In particular, we have this j here. What is j root of minus 1? We have this j here. What is the meaning of this expression? Extremely abstract. Let me go ahead with the calculations. Let me show you that this formal expression, really abstract, totally abstract, has a meaning, a physical meaning, which can be expressed also more explicitly in mathematical form. Now I do the product. This multiply this, plus this multiply this, plus this multiply this, plus this multiply this, plus in sense of algebraic. We can see 1 divided 2, which multiply this expression, the exponential expression, plus j root of 3 divided 2, which multiply this exponential expression, plus 1 divided 2, which multiply the exponential expression, and at the end, this element here, which is minus j root of 3 divided 6, multiply this expression. Easy. Distributive property of the product with respect to the sum. Look at this. I can organize these 4 elements in an interesting form. Which one? Here was mixed real and imaginary. What is the idea? The idea is to separate the real part, the real contribution part, let me say the real contribution with the imaginary contribution. I do the calculation as I already explained, and look, what I am doing is to considering everything which is real. We can see this is real, real in the amplitude. Let me say this 1 divided 2 is real. This is imaginary. That don't belong to this one. This is real. This is imaginary. This means this element here and this element here can be, let me say, expressed in this form here. No? I put in evidence 1 divided 2 here, 1 divided 2 here. It remains the sum of these two exponential functions. Plus, here is the same. I put in evidence j root of 3 divided 2. And I will have this expression here. 1 plus, because you have a plus, 1 minus, because we have minus. But please pay attention that the exponential function, they are not the same. Otherwise, I can cancel. Otherwise, I can sum here. We have here minus, we have here plus. Very important. Now, I will hold a lecture about these two equations. Very important. Or Euler equations sometimes. But I would like to put a plural if you don't mind. Okay, this is an Euler equation. This is another Euler equation, let me say. But let me say plural. I don't know if you remember math, but I will hold an interesting lecture because it's connected with differential equations, it's connected with dynamics, it's connected with the course, let me say. But let me at this moment assume these two very important equations as valid. Cosine of phi, cosine of something equals exponential function j something phi in our case minus exponential function minus j phi divided to j. Yeah, for sinus of phi. For cosine, we have basically in the numerator the same expression, but instead of minus, I have a plus. The denominator change. Instead of 2 times j, we have a 2. I will demonstrate during the next lectures mathematically because I have a nice demonstration using differential equation. This means using dynamical somehow system. If you trust me, if you trust Euler with these expressions or the formulas, we have cosine of something which is equal to this one, sine of something which is equal to one. Now, please pay attention here. This something or this phi, in our case here is, in this part here, is root of 3 divided 2 multiply t. Because it's the same. Once with plus, once with minus. Exactly like here. Exactly like here. Plus is also plus here. 2 is also 2 here. This means I can write, if these two equations are valid, as cosine of root of 3 divided 2 multiply t. Cosine of phi, because our phi is root of 3 divided 2 multiply t. Look at this equation. What about the rest? I have to tell, but you have seen that from here to here, from here to here, I put in evidence, I didn't tell you, but from gymnasium, I think it's clear. No? I put in evidence exponential function minus 1 divided 2t, which basically is here, is here, is here, is here. I don't know if it's visible. The product of two exponential functions is one exponential function up to the sum of the exponent. Basic knowledge. What is the result? I don't know if you remember. Exponential function up to x multiply exponential function up to y equals exponential function up to x plus y. Do you remember this? Of course, this multiply this multiply this. I will obtain this one, and this multiply this plus this multiply this, I will obtain this. Now, this I already explained. Why this is sinus root of 3 divided 2? Because looking at this equation here, we have plus minus. Exactly here, minus, let me say in front of minus, plus in front of plus. Plus in front, let me say in front just to understand, plus 1 which multiply this expression which you have a plus j phi. It's exactly the same. No? This minus and this minus is here, this minus of this minus. Here we didn't have problem because it's plus everywhere. Divided 2j is sine of or root of 3 of multiply t, because this is our phi. Now the last question, where these two j come from? If it's not here, this is easy. Somehow, we have seen before that if I multiply by j numerator and denominator, we will have a -1 and j6. Now, 6 here is obtained considering the product of 3. I don't know if it's visible. This minus here, we will change this in plus. You can see here, plus with respect to plus here, you can see here. And we will change this plus in minus, where we have this minus here, which is here. Think about to put in evidence exponential function -1 divided 2. I did relatively quickly because I know that you know from high school, but redo at home these calculations. Or see again in the presentation on YouTube, or download from my statistics material. At the end, we have this element here, which is common here, this is common here, which multiply cosine of this, plus root of 3 divided 3, which is here, multiply sine of root of 3 divided 2. Now, we can see many things here. We can see that from a really complex exponent, complex in the sense also difficult to be interpreted, using complex value, excuse me for this two words which I am using with different meanings, we have now something time, which can be easy to be interpreted. We have a pulsation, let me say in a frequency. You remember math, no? We have an exponential function with weight, this mathematical expression. Look what we have. I copy for you again this expression. You remember the pulsation, or if you want, you can call omega frequency, even though omega is equal to pi f. No? This means the frequency is this expression divided 2 pi. No? But anyway, sometimes we call this frequency because it's just in a proportional. This means we have a function which is in a combination of sine and cosine. This means it's in a function with the same frequency, because we are cosine and sine, they have the same frequency. Why is going to 0 with oscillation? Oscillation because we have a trigonometric function, the sum of two trigonometric functions. It's going to 0 because it's weighted by an exponential function, which for t toward infinite is going to 0 with oscillations. Meaning of this, that the energy, the free energy which you have inside, is an energy which is in time oscillating. Let me say, you see free is oscillation with this law, but also any kind of variable, state variable, or also the current in the resistance. Now I show you free current of the resistor. Voltage, I don't know, voltage you see, I've seen voltage in the inductor with different initial value, but nevertheless with the same frequency, I can demonstrate now, will go into to 0. Why that? Physically. Because the energy will be dissipated and go away. Why remain the same frequency? Here, also, I can improve this. If you think in math, you can consider just a sine or just a cosine with this frequency and the phase. It's in a phase. I don't know if you remember what we can do, but it's not necessary to do it. in order to see very well what happens. No? I mean, try to calculate at home. Be such that it is possible, no? If you remember a little bit math. I don't know if you remember. It's the same expression. Remember with arcotangent. Try to remember the form. Now, why when I have to, for instance, calculate the current IC, we have a basically in a similar structure, because, for instance, this is C times. This is an exercise. No? Let me formulate another exercise. This is an exercise. Try to calculate EC, for instance. I mean, to calculate IR is extremely easy, because it's exactly what I have, divided R. This means this is enough to divide by R this expression, and we have IR. Exactly. As I told you, the energy in the dynamics, or better to say, how change the energy over time for all possible variables, is reflected here in our case, but can be reflected also in any functions which I find, any elements, any variable which I introduce. Basically, as I told you, we calculate the states because they are, let me say, directly connected with energy, and then we calculate all the rest. Try to calculate EC equals C time, of course, free, no? EC free. We are always in the case of free, C free. It's not so difficult, because you have to multiply by C, which you know, this is 1. Multiply the derivative of this. It's a little bit boring, no? These two, let me say, to be calculated. It's a little bit boring, but it's possible. It's easy, no? And then conceptually. Let me see other possible. Other possible question. It's possible. No? I do the derivative of this, boring. I multiply by C. Clear, in accordance with the, yeah. If I want to calculate I1, it's easy. I1 is equals IR plus IC. Both, I already explained how I can calculate. This is extremely easy. This is boring. The sum of both is I1. Once I have I1, I can calculate UL with this. L multiply the derivative of I1. Of course, it's boring, but conceptually it is possible. Very important, the frequency of the signal, this means, let me say, qualitatively, the profile does not change the amplitude, but the frequency doesn't change. Because you remember, the derivative of cosine of this, for instance, is minus sine of the same, let me say, argument, multiply root of 3 divided to change the amplitude, but not the frequency of the pulsation, if you want, or pulsation. Okay, I have just 5 minutes. I would like to introduce an exercise which should be done at home, and then next week I will complete. Even though I notice now that in my study it's not a problem, because it's just this slide. This means we will see a little bit together what we can proceed. But you can look also at this approach, which is exactly what I already told you for different other cases, but of course here a little bit more complicated. Complicated not, but includes the case include different more general considerations. Look at this. Try to do at home, and next week we will try to solve together. Calculate the force. This means sometimes I am writing very quickly. Answer, considering, please pay attention now. U of t, until now we have a seen constant, you remember? T, which multiplies sigma of t. About the sigma, I will tell you now, and next time in more in detail. Sigma represent is an interesting function. This means 0 for t less than 0, and 1 for t equal or larger than 0. This means represent exactly the time which I am starting. Just to introduce a new concept. At this moment, until now, we didn't consider this way to express. In fourth problem, yeah, I wrote correctly. We changed the notation. Yeah, I forgot again. Excuse me for this. Sometimes I'm writing very quickly because otherwise it's really too heavy to go at the end of the lecture. Multiply equals this as an input. We can see that the forcing variable is the linear function of the time. This means I am starting from 0. Sometimes some authors didn't put this, but for engineers is important. For engineers is important this notation, because this notation indicates when exactly we start. At time 0 is 1, and remain 1 for time larger than 0. Before time 0 is 0. This means define it exactly the fourth answer starting from 0, which is our starting point. Okay, I don't want to anticipate here anything, but just this. Because do you remember, I told you already many times that the UC force consists of a part quite similar with respect to the free answer. Why that? Because if I put this on the other part, we have this expression here, minus t multiplied sigma equals 0. This means I can assume that the part of the solution is basically, we demonstrated to this. Do you remember once with the calculation? It's exactly the same with different combinations element, because we have a different initial conditions, basically. Plus, algebraically plus, but could be also minus, plus something we takes into account of this element here. Yeah, it's a shame I forgot to print to scan the rest of the solution, assuming that I find the rest of the solution. If I don't find, we can redo alone. Let me nevertheless show this aspect here. Why I am supposing that this tilde C, this particular form of the solution, we takes into account this contribution, consists of this form here. We have seen, I think, once. We have seen that we can start with the hypothesis that this particular function takes into account the nature of the input. This means I can start directly with this. Please pay attention. It could be not enough. This depends on the system. Could be not enough. It could be that this tilde depends of t squared. This we will see during the calculations. In this case, it is enough because we have a feedback between all states. We don't have a floating integral in the block diagram. I will clarify next week. We have time to do that. Here is interesting this time because if I do the derivative, we have here the derivative of this sigma, which is delta. About delta, I didn't tell you until now. Next week, we will consider in detail this sigma function and this delta function, delta of Dirac. I don't know if you heard about that. At this moment, we didn't define this. I told you this function is a little bit more difficult to be defined, but I have a material to consider also this function. Okay, you can look a little bit with this material here, and then we will go ahead. If I find the rest, I will scan. I will put in my study. Otherwise, we will do by hand. I will do by hand the rest. Think about this kind of problem. Interesting two things. This T. This means the voltage input is increasing over time. And this sigma here states, in our case, let me show you concretely so we can understand what I intend. States the switch at time 0 is going on. Typically, we can do a different formula in order to represent both. Forced, if I close here, position 1, and free if I close in position 2. This sigma state exactly in the switch. Of course, in free, we don't need. Why that? Because it's 0 multiplies sigma. Because I am, what is the free answer? I have energy here, I have energy here, and I close here in short circuit. This I told you, no? Because U of t is equal to 0. This means I don't need to consider this sigma function, which state exactly when I start. Okay, we will do together nevertheless this fourth, and then we will go ahead with theoretical and theoretical. Theory is not so much because the time which we have is not, but methods, ideas, exercise, interpretation of of our representation in terms of dynamics, in terms of dynamical systems. Okay, it could be that I have to accelerate a little bit, but anyway, I am here for your questions. Now I stop the lecture. I am here for your questions. Typically, after the lecture, I have a time. At each lecture, I have a time for the students. Otherwise, send me an email to answer questions, any kind of questions. This material is in my study. Now we will go ahead to next week, 8:30. No, we have this 15 minutes in addition. Thank you. Thank you.